Hello, once again. We will be giving you a video lecture over a chapter of General Chemistry 2. Now, these sets of videos will be over chapter 13, dealing mainly with colligative properties. Which is essentially the properties of solutions. How do solutions act that are different from the pure liquids? This first video will be about essentially what makes solutions different and some of the factors affecting them. And then the second video will be largely about ways we will measure concentrations of solutions. And the third and final video will be focused on colligative properties, which are the properties that these solutions contain. Let's go ahead and get started. Now, basically, this chapter will deal with why do we salt the roads, for example, when it snows? Why does salted snow melt while unsalted snow doesn't? So the first thing we need to talk about is solvation. We've previously discussed solvation when we talked about this in general chemistry, when we talked about aqueous solutions, but now we need to re-hit this, especially with the terms solution, solute, and solvent. So when we talk about a solute, it is the object which is being dissolved. It could be a solid, could be a liquid, could be a gas, but is the thing that is being solvated. The solvent is the larger concentration thing that does the solvating. It's the one that surrounds and dissolves or solid, liquid, and gas. We most often assume the solvent is a liquid, but a gas could technically dissolve another gas, or a gas could dissolve a solid, or what have you. So there's different situations where there's a solid solvent. Solid dissolves a liquid. A solid dissolves a solid. A solid dissolves a gas. And all those. So solvent doesn't have to be a liquid, but typically it will be. And when we talk about the solution is the sum of all the parts. What happens when the solute and solvent combine? Now, when we talked about this in the aqueous reactions chapter, we talked about the idea of precipitation reactions or salt metathesis reactions, essentially reactions that formed insoluble salts. Now, we didn't really explain why this happened, why a solid would form or wouldn't form. We just said these are the rules, here's a chart, let's use that. But the idea here is that in order for solvation to occur, we have to break up certain intermolecular bonds and make new intermolecular bonds. The solute is usually bound to itself, whether this be as an ionic solid with a bunch of ionic bonds, some sort of covalent network solid with a bunch of covalent bonds, or maybe a molecular solid or metallic solid. Now, some of these have weaker bonds, some of these have stronger bonds. The solvent is usually made up of a bunch of intermolecular bonds, intermolecular forces. Well, in order to form a solution, we must break apart all of the intermolecular solute bonds and break apart some portion of the solvent intermolecular forces. So this takes energy. We're stripping the solutes away from other solute molecules. We are separating the solvent from solvent interaction, which may be a very strong interaction. But we are replacing them with new solute-solvent interactions. Ideally, the energy of these new solute-solvent interactions will give more energy back to the solution than was lost to break the bonds. Now, this process is encouraged by a new energy that we're going to talk about called entropy. We will focus on this energy called entropy later when we talk about thermodynamics. But entropy is the energy of mixing. It is the energy of randomness within the molecules. That rather than keep A and B separate, it's a lot easier to allow them to intermingle and mix together. And there is a certain energy that comes when these guys are mixed together that is more advantageous than just keeping them separated. So this mixing helps, as well as the fact that even though most of the solute bonds may be stronger than the solvent-solute interactions, there's a lot more solute-solvent interactions that can be made. So we can make a lot of lower energy bonds that end up greater in the long run. So, however, this is the big thing. However, if the intermolecular forces between the solvent and solute are too dissimilar, they're too different in relative strengths, the solute and solvent will not mix, which will get the aphorism like dissolves like. That doesn't mean necessarily the solute is stronger than the solvent. Sometimes the solvent is stronger than the solute. When we have ionic solids that don't dissolve, because the ionic bonding that is made between the cation and anion pairs are stronger than any solute-solvent forces that we can make. And so while we might be able to break apart a little bit of solute, very little actually breaks apart. Now, when you have things like oils that only have London dispersion forces, those guys are very easy to break apart. However, because the solvent must stop interacting with other solvent to make these new solute-solvent forces, the loss of energy from breaking and disturbing the solvent-solvent interactions are not worthwhile. It is very easy to break apart the oil, but the water doesn't really want to deal with it. It's not worth its time. And so the water or other solvent doesn't want to dissolve the oil, and so that's why you get the mixtures. So like dissolves like. So polar things usually dissolve polar things. Non-polar things usually dissolve non-polar things. So, I've already talked about this a little bit. So things like if the ion-ion or ion-dipole intermolecular forces are too strong, we get poor solubility. But this also explains why sugar, ethanol, and diethyl ether can dissolve in water, because water has a bunch of hydrogen bonding, and these guys have dipole-dipole or hydrogen bonding intermolecular forces, and when they're put into water, they can generate more hydrogen bonding with water. But as I said, this also explains why hydrocarbons like hexane will not dissolve in water. That the London dispersion forces may be weak, but the hydrogen bonding of the water is strong, and so it won't easily break up. Now, as I said, there's an energy of mixing. We can calculate this. We usually won't, but it is possible to calculate this as an enthalpy of solvation. How much energy does it take when something is dissolved? We can measure this with our bomb calorimeter. Actually, not bomb calorimeter, but our standard calorimeter, or constant pressure calorimeter. that if you simply put that 2 coffee cups together and pour a solid into a solution, into a solvent, we can measure the energy loss or the energy gain when it dissolves. So we're looking at, okay, we have to break up the solute-solute interactions as it dissolves. We have to break up some portion of the solvent-solvent interactions, but depending on how much energy we get from the new solute-solvent attractive forces, we could get a exothermic dissolution process like hot packs, or you can get an endothermic process where it ends up somewhere a little bit higher up, like cold packs. That it will still function, it will still react because of the entropy energy that will be generated. But they will have to absorb some energy from the surroundings to help with the reaction. So this endothermic mixing is favored when we have a large increase of entropy. Most salts do end up having a endothermic solvation energy. Now, along with this, we have a concept called saturation, because solubility is a reversible process. That energy can be generated through dissolution, but if we put that energy back, we can also reverse the process. So if it's an exothermic process to go forward, it can be endothermic to go backwards. So when we talk about the forward process, we can talk about solvation or even hydration. But the reverse process is our crystallization. And the idea here is that for every given solution, there is a maximum amount of solute that could possibly dissolve in a given quantity of solvent at a given temperature. And this is our solubility. It's because the water has to hydrate so many molecules, so many of these anions or cations or molecular pairs, and we need so much water to do that. And this water then helps separate the cations and anion pairs and keeps them from seeing each other in solution and thus snapping together and recrystallizing. But if there's not enough water to fully hydrate and solvate everything to what it needs, some stuff will not dissolve. So when that maximum is reached, the solution is said to be saturated. So sometimes we'll use saturated sodium chloride solution, which will have some crystallized sodium chloride floating in the bottle, or saturated sodium bicarbonate. All that means is that we've dissolved as much as we can, and we've maybe added a little bit of extra just to make sure that it stays saturated. So no more will dissolve at this temperature. Any solution that is below this maximum is said to be unsaturated. But a neat thing happens. Since solubility is temperature dependent, it is possible to get more solute to dissolve than is typically possible at a given temperature. So it's like saying I have 10 pounds of rocks in a 5-pound bag. It's overstuffed. Now, this is only possible because the solution crystallization has a small amount of activation energy needed to start a process. And if a solution is somewhat stable and it doesn't have enough ambient energy to crystallize, it will stay in this supersaturated solution. So what you do is you saturate a solution at a hot temperature, and then as we allow the solution to cool, the solubility will decrease. And so what was originally even, now the solubility is decreased, and so we're up here in the saturation process, but down here in the solubility. And when you give it that little bump of energy, whether it's simply shaking it real good, dropping a single crystal, giving it a stir, some way to agitate the solution, give it just enough energy, it will rapid crystallization. It will rapidly crystallize until the whole solution has turned into a solid. So that's a really neat thing to see, but not necessarily super important. Now, there's factors that affect the solubility. Obviously, the first one is the intermolecular forces, but there's also pressure and temperature, one of which we've already kind of briefly discussed. So we've already discussed intermolecular forces partially when we talked about like dissolves like, but the idea is that the two liquids need similar intermolecular forces. If we start to get greater and greater differences, we lose solubility. Now, so take a look at this. So we have methanol, which is a 1-carbon alcohol. It is infinitely soluble in water and slightly soluble in hexane. Take about ethanol. Ethanol is a 2-carbon alcohol, infinitely soluble in water, infinitely soluble in hexane. Then you get propanol. Propanol is a 3-carbon. It's infinitely soluble in both. And now as we get to 4 carbons, it's a lot of London dispersion forces and a very little polar end on the end. It's now slightly soluble in water, infinitely soluble in hexane. Pentanol, it's even less soluble. Hexanol, 6 carbons, it's even less soluble. Heptanol, it's almost negligibly soluble at this point in water, and very soluble in hexane. So when two liquids mix together perfectly with no solubility limit, they are said to be a miscible solution. So methanol in water is miscible. Ethanol in water and ethanol in hexane would be miscible solutions. However, when these two do not mix very well at all, this is said to be immiscible. Now, when this happens, we often see the formation of two visible layers that will form up based on density of these mixtures. And with that in mind, we can easily separate these via gravity. So you see in the separatory funnel over here, we have dyes that is dissolved in various layers, probably one blue dye, maybe aqueous, might be in a chlorinated solvent layer. You might have a white dye and aqueous layer, and a red dye in the organic layer. That the organic doesn't really mix with the aqueous at all. The chloroform doesn't really mix with either. The chlorinated solvent, slightly polar, but mostly London dispersion forces, and highly dense. And so you could separate them by letting it drain out the bottom and capturing each layer individually. But generally speaking, the more similar the forces, the greater the solubility. So, now, pressure effects. Please note, pressure only affects the solubility of gases. Pressure only has an effect on the solubility of gases. A liquid and a solid are non-compressible. You can put pressure on a solid and a liquid, they do not change. cannot crush a liquid down to a smaller size. A gas can be crushed down to a smaller size. It has an indefinite volume. So pressure only has the effect on the solubility of gases. But generally speaking, remember what we talked about last chapter about vapor pressure, that we have kinetic forces that are making a gas escape, intermolecular forces that are capturing it, and that when a gas has enough energy, it can reach escape velocity and escape from solution. But if it bumps into solution again, it can be trapped. Well, since they need kinetic energy to transform into the liquid phase, the same thing can be said about keeping them soluble. The greater the pressure above the liquid, typically the greater the solubility of that gas in the liquid. So if there's a bunch of gas pressure pushing down, it's harder for the liquid to escape into the gas phase. It's harder for any gases dissolved in that liquid to escape into the gas phase. That is pushing it back down. Also, if it's the pressure of the gas in question, there's more of those gas molecules bumping into solution and thus dissolving into solution. So this effect can be described as Henry's law, that the molarity of a gas, so the concentration of a gas in solution, is directly related to a gas constant for that gas and that solvent times the pressure of that gas. So the units of K sub H is going to be molarity over pressure. So it could be molarity over pascals, or molarity over torr, or molarity over bar, or atmospheres, but that will tell us what pressure we need to use for the gas. So there's a direct effect of the pressure goes up, the molarity would also go up. Now, temperature has a unique effect. Temperature is a little bit difficult, and this is where we'll finish this video. That temperature has the same effect on all types of solutes and solvents, but it affects them in different ways. Temperature has a direct correlation on kinetic energy. That kinetic energy can be applied in different ways. So in solids and liquids, most solids and liquids increase solubility with increasing temperature, because increasing kinetic energy makes it easier to break up solute and solvent interactions. And so if we can break up these interactions, we can overcome the activation energy barrier, it's easier to make these new solute-solvent interactions. So more kinetic energy means they can bounce around and mix up better. However, this only works if the energy of mixing isn't exothermic. Energy of mixing is endothermic. If this reaction is exothermic, the temperature will have the opposite effect, but many of them are endothermic, so we don't have to worry. Now, gases will always decrease in solubility with increasing temperature, because, as I said, kinetic energy is directly dependent on temperature. If gases need to achieve escape velocity to escape from solution, higher temperatures means greater kinetic energy, which means more portion of the gas can escape as a vapor. More of the gas has achieved escape velocity. So with that in mind, gases always decrease in solubility with increasing temperature. So a hot soda will go flat faster. You open up a soda that's been in the car, It's going to fizz and bubble a lot more and go flat a lot quicker than, say, something you've put with ice and refrigerated, because it will still go flat, but at a slower period of time, because the solubility of the carbon dioxide is much higher when it's colder. But that's where we'll stop this first video.